covered similar to it, but you have to, I want you to go through the process. So this is what is the integral of 4 times the arc cotangent of x. And again, this is not one that is obviously a integration by parts. We don't have the integral of the arc cosine of x. We have the derivative of the arc cosine of x. So just like we didn't have the integral of the natural log of x, but we did have the derivative. You can use integration by parts to find the integrals of the arc trig functions. So remember that the derivative with respect to x of the arc cosine of x is equal to negative 1 over the square root of 1 minus x squared. So that, it's in that table, so I'm not asking you to remember, but the arc derivative of the arc sine was positive 1 over the square root of 1 minus x squared. The derivative of the tangent was 1 over 1 plus x squared, and we mostly use the integrals. The integral of this equals that. Okay, so we know that. So again, what you're going to do is you're going to choose u, and you're going to choose dv. And just like when we had the natural log, when we're doing the natural log, we know the derivative of this. We don't know how to integrate it, so it doesn't help as much to make this dv. So we're going to let u equal the arc cosine of x, and dv, we'll move the 4 out, so we'll just do 4 times the integral of this. So we'll do the integral and then multiply it by 4. So dv is just dx. So then you need du. So du is equal to, well, it's equal to that times dx, and dv is equal to dx. So I didn't write that. Yeah, so dv equals dx. So here we had u is equal to the arc cosine of x. So the integral of dv is just v, and the integral of dx is just x. And again, we don't put the arbitrary constant in there. So now we have everything we need. We write down the integration by parts formula. U times the integral of u dv is equal to u times v minus the integral of v du. So all we have to do is go back here and find all the stuff we need. So there's u, there's du, and there is v. So we do that twice. So we just plug them in there now. So we get u, which is the arc cosine of x, times v, which is x, minus the integral of v, which is x, times du, which is negative 1 over the square root of 1 minus x squared dx. And we'll just move things around. So I'm going to move the constant here to the front, even though I don't need to, but I'm going to do it anyway. And you can see what happens in the second term is we have the negatives cancel. Well, yeah, the negatives cancel out, so it becomes positive. And then you have the integral of x divided by the square root of 1 minus x squared dx. And hopefully we can do this integral, which we can. So why don't you do that? So you're going to let u equal 1 minus x squared. Du will be equal to negative 2x dx. We had this on our last test, right? The first problem was something like this. I don't know if it might have been x squared minus 1 instead of 1 minus x squared, but it was close enough. Oh, I'm just doing, yeah, well, we do the 4, but I'm just doing the integral of this part. So once I get the answer, I'll multiply it by 4 to get the right answer. So it doesn't mean integration by parts, sometimes you have to use u substitution again, but or again, we're already using u, but as long as you can keep your u's separately. It's like physics, we use T for Tesla, and we use T for period, and we use what other other things. We use the letter more than one time. You just have to make sure you keep it in the right context. So I did my birthday, the thing we did in class yesterday. I did it in my other class, my 10 o'clock class, and it worked again. So 6 out of 6 times I've done that little experiment. There's at least 2 people have the same number. So we got to get all the governor's school together. That would be enough people to actually have 50 people. We could do the birthday trick. Okay, so there it is. So, not surprisingly, we end up with negative the square root of 1 minus x squared. So the 1/2 that we get from doing the u substitution cancels out with the 1/2 that we get in the denominator from integrating x to the u to the minus 1/2 by adding 1 to the exponent, dividing by the new exponent. And then the original problem was 4, so I multiplied everything by 4. And you look at that and you think it's surprising. It's if I take the derivative, I end up with that. But it's true. What would happen is you'd have to use the product rule here. So you'd have x times the derivative of the arc cosine, which is going to be 1 over negative the square root of 1 minus x squared. And then you'd have the derivative of this times the arc cosine. And it turns out the first one, 4x times the derivative of the arc cosine, once you've simplified it, cancels out with that. And what you're left with is that. Okay, so that's basically what happens is when you do the product rule, if you take the derivative, 1/2 of it cancels out with this thing, leaving the part b. Just when you take the derivative of x, you get 1. Okay. So I'm going to move back here. I'm going to let you do a few here yourself. So we'll do this one. We'll do this one. This one's too easy, so or not different enough. So we'll do this one first. So again, the rule is u is part of the original integral whose derivative is simpler than the original function, and dv is a function that we can integrate using the integral tables. And you might say, well, I can't do e to the 2x, but you can, because you'd have to use the u substitution. So when you integrate e to the 2x, does anybody know what we get if we integrate e to the 2x? Remember we talked about that? It's either 2 e to the 2x's or 1/2 e to the 2x. What do you think, Seth? Yeah. So when you integrate, you divide by that constant. If you took the derivative of e to the 2x, it'd be 2 e to the 2x. If you integrate it, it's 1/2 e to the 2x. So go ahead and do that. And if anybody has any questions, just ask me while I'm wandering around. Let's see, I have Christian's papers here. Yeah. So I made up the test yesterday. So it's going to be challenging, not impossible, but it's not going to be. Put a little fear in you. Yes.
Which one was it you said that you wanted to put the one that has the photo integration?
Yeah, the dv is the integral, the hardest integral that you can actually do using the tables, which would be e to the 2x. So dv would be e to the 2x dx, and u would be x, because the derivative of x is 1, which is simpler than x. So it satisfies both requirements. So yeah, it took me 22 minutes to take, which is and also the review is, I think I said in my email, it's not very long, so don't wait till the last minute and think I'm going to tell you how to do everything in the review. The best thing to do is to what you did last night or yesterday and the stuff I'm handing back today. If you understand how to do those, then you shouldn't have any trouble. Two of the problems, you have to set up the integrals, but you don't have to do them. 3 of them, you actually have to do the integrals. Oh, I was going to walk around and see if anybody had any questions. See how we're doing. No, let's see what you got. Didn't know where you were with the whole thing. Okay, so that's correct, and that's correct. So you get x times there, integral of that, and you do that. Very good. Okay, so you're going to you have to decide one part to be u, which is x, and then the other part is dv. Just x, not this x right there. You put 2x. So it's not the exponent. It's not like u substitution yet. You're getting ahead of yourself. So this part of the product, this is u, because it's the derivative of x is 1, which is simpler. So that's what you're looking for. And then dv is this second part. So dv is equal to e to the 2x dx. Okay, which you can integrate, that we were just talking about then. You can use use substitution, but the integral of e to the 2x dx is 1/2 e to the 2x, so that'll give you v, and then you can do the derivative of that. Will give you the du part. So you got an answer yet? I think you do. Yes. Okay. Okay. Looks like doing pretty good. Get the seat down. Oh, it just went up. No, that's even worse. That's one lesson I've learned many times in life. A lot of times you do things to try to fix them and they just get worse. You ever had that experience, right? If you ever own a home, you experience that all the time. And you have to decide at what point do you call on the professionals. And these days, I call on the professionals a lot sooner than I used to because of my experience with. Unless you do it, unless you have a reasonable amount of experience, chances are you're going to mess it up. Okay, so I'm just going to do this here, show you what we get. Yeah, I think I may have noticed I didn't catch some of you. I think you might have missed a factor of 1/2 in here, but. So the answer is 1/2 x e to the 2x minus 1/4 e to the 2x plus c. And so you get 1/2 from when you integrate the first time to get v, and then when you integrate this again, you take the 1/2 out, which is that 1/2, and then the integral of e to the 2x is 1/2 e to the 2x. So you end up with a 1/4. So what do you think, just based on looking at these two problems, what do you think the answer should be for this second problem? Just write it down. Don't go through the whole long process. Let's see if so Lexi, what do you think? Well, think about the, where did the 1/2 come from? The 1/2 came from integrating e to the 2x, because you end up with when you solve for dx, you get du over 2. So now I'm integrating e to the 3x. So I should divide, instead of by 2, I should divide by 3, right? Right. So the first term, instead of being 1/2 x e to the 2x, is going to be 1/3 x e to the 3x. And the second term, you can see how the 1/2 comes in twice. So if you instead of having a 1/2, you have 1/3 twice. What would be that? 1/9. Yep. So you get 1/3 x e to the 3x minus 1/9 e to the 3x plus c. Okay, let's find one where you have to do integration by parts twice. We've already done that one. Well, we haven't done this one exactly. Yeah, well, let's do this one. Well, actually, even before we do this, let's think about how might we simplify this problem even before we start. Yes. Pardon me? That would be the normal way. I mean, ultimately, because what you're going to have, so you know, we had the previous problem was the natural log of x. We still let. So what you're saying is you would, well, you actually don't have to use it for u substitution. What you'd say is u is the natural log of 3x, and dv would be equal to dx. So when you take the derivative here, and you take, obviously this one's easy, integral of dx is x. So when you take the derivative, what could I do there before I take the derivative? Could I use the properties of logarithms to change it somewhat? I mean, it doesn't make a huge amount of difference, but how could I, what is the natural log of 3x? It's the natural log of 3 plus the natural log of x. So if you take the derivative of the natural log of 3, well, that's a constant. So you just end up with 1 over x dx. And you're like, well, what happened to the 3? What if if I use the chain rule, you know, if I said f of x equals the natural log of 3x, and so then you could use the chain rule, you know, f of u equals the natural log of u, u of x equals 3x, and if I take the derivative like that, I get 1 over u, and when I take the derivative here, I get 3, and then the chain rule says f prime of x equals f prime of u times u prime of x. So I get 1 over u times 3, but u is 3x. So I get 1 over 3x times 3, and the 3's canceled out. And you get 1 over x, which is what we got here. Okay, so so the question is, could I do that initially? And how would that affect something? Because I'm thinking about it, and I'm like, yeah, I could. I mean, that's the way to solve the problem. I mean, the ultimate answer here would be you take u times v, so we'd have x times the natural log of 3x minus the integral of v du. So that these cancel out, so you just end up with the integral of dx. So you get x times the natural log of 3x minus x plus c. What I was thinking about was, I wondered what would happen if you used the properties of logarithms initially and said you have the integral of the natural log of 3 dx plus the integral of the natural log of x dx. So I break it up initially by saying that the natural log of 3x is the natural log of 3 plus the natural log of x, which I use there. So if I integrate that, the integral of the first part is going to be the natural log of 3 times x, because this is a constant, so you can bring that outside the integral. And then you integrate dx, so you get that. And from previous previous work, we know the integral of the natural log of x is, let's see what it was, somewhere back here, there it is x times the natural log of x minus x plus c. Okay, so hopefully I can remember that. So the integral of the second part is x times the natural log of x minus x plus c. And I look at this result, and it's not the same as that result. But what you can do is you could factor out an x, so you'd have the natural log of x times the natural log of 3 plus the natural log of x minus x plus c, and then you could combine these two together, so you'd have x times the natural log of 3 times x minus x plus c. So you do get the same thing. It's just you have to, so anyway, it shows you can use the probability logarithms if you want to, or you don't have to, and you're going to get the same answer anyway. So, okay. Yeah, why don't you try that one there? Because this is kind of different. I don't have x squared, so it's not a multiple. It's not a multiple step. So the question you might ask is, is there an integral formula in the table for the integral of secant squared of x dx? Anybody know what there is? Does anybody know what the integral of secant squared of x is off the top of their head? Yeah, it's a tangent, because the derivative of the tangent is a secant squared. So this really is kind of like the last problem, except instead of you're going to let u equal x, and you're going to let dv equal the secant squared of x dx, with the knowledge that in the integration tables you'll find out that the integral of the secant squared of x dx equals the tangent of x. So there's your formula to allow you to do that integral. So I'll let you do the rest of it. I'll give you 5 minutes head start. I mean, your initial, sometimes you kind of try to get ahead of yourself too far, and the first thing to do is to see whether the integral exists, because we don't use that very often, and so you may, if I saw sine or cosine, you'd say, oh yeah, I recognize that, but there are other integrals that are in the tables that we may just not use enough to recognize. Decided to get myself a new phone. My charger's not working. My lightning connection, there's something inside there. It's not working. So I finally decided to, but don't get excited. It's not an iPhone 10. I still want it to fit in my pocket. Yeah, last night I was like wiggling it. I said it's time to give up on this thing. And I'm going from 8 gigabytes to 132 gigabytes. This is going to be exciting. I don't have to keep uninstalling apps to have enough space on my phone. And I could take pictures without having to erase them half the time. Oh yeah, so you're gonna have to know what the integral of the tangent is. That is in the book also. Yeah, what is the integral of the tangent? I don't have my book with me, so let me think about that. Integral of the tangent dx. So that's the sine of x over the cosine of x dx. So if I let u equal the cosine of x, du equals negative the sine of x dx. So I get, when I integrate, I'll get 1 over u times negative du. So that's going to be negative the natural log, the absolute value, the cosine of x. So that's the answer. Okay. So if you had your integral table, the integral of the tangent of x dx is equal to negative the natural log of the absolute value of the cosine of x plus c. So when you get to that part, you'll have the integral. I think that's right. Yep, that's right. Okay, so there's your answer. So we integrated secant squared to get tangent to get v, but then we had to integrate tangent, which was also something that was in the tables. And the negatives cancel out, so we negative here, negative, you get negative from the integral of the tangent. So that's that. Okay. Before I forget, I'm assigning the homework for this section because we're almost done. It's time to face the music. Oh, yes. Okay. So I'm going to start on the last example. Where the heck did all these... Where is my homework? Oh, here it is. So those are your homework problems.
So when is this due?
Next Friday.
We're not going to do this.
Oh, that's right. Thanks for reminding me on that. By the way, you're not having class next Friday. Yeah, I sent an email to Mr. Graham. Well, you're not going to be here because of something else. Or was you because we're not having school next Friday?
Well,
By the way, we're not having school next Friday. You're off next Friday. So where are you guys going?
well, I'm going to get my schedule for next year.
Oh, at Jefferson? Yeah, okay. Anyway, so nobody has class next Friday, so it's due the Monday afterwards. The reason we're not having class next Friday, it is our first professional development day that's been built into the schedule, and pretty much nobody else except myself and Mr. Pell have classes on Friday. He has some developmental math classes. So everybody else usually doesn't have a class on Friday, but so we're going to cancel your class so that I can go to this professional development day. So enjoy Friday off next week. And I let Mr. Graham know. I remembered last night. I said he may not even know. So, okay. Actually, I'm going to do work. I'm going to start on one more problem. I don't know whether I'll get all the way through. So we pretty much handled everything. We'll do where you have to do integration by parts twice next time. But for right now, I want to look at this case. So what you have is not a product of x times some trig function or e to the x or all the other things that we've looked at. We actually have e to the some constant a times x times the sine of some other constant b times x dx or cosine. Now the question is, do you let u equal, well, here, that's the answer here. You let u equal the sine or the cosine, depending upon which form you have. And you let dv equal e to the ax dx. But they're like, well, you said that u had to be a function that got simpler when you take the derivative, but I don't think the derivative of the sine, which is the cosine, is any simpler than what I started out with. So just like yesterday when we did our little our experiment with the numbers, it's not obvious, but it does work. So let me just show you how this works. So I'm gonna use this as an example. So we have e to the 2x times the sine of x. So as I just told you, we're going to let u equal the sine of x, the sine part, and we're going to let dv equal e to the 2x. So the derivative of the sine is the cosine at our dx. V is the derivative of, or the integral of this. We just did it. It's 1/2 e to the 2x. So we plug that in. So we say that, you know, the integral of, in this case, u dv is equal to u times v minus the integral of v du. So I'm going to put that in there. So u is sine of x. V is 1/2 e to the 2x. And then I'm going to subtract the integral of v, which is 1/2 e to the 2x, times du, which is times cosine of x dx. And you're still not convinced that it's going to work out right, because you say, well, I'm back to the same thing. I've got this integral of two things, you know, I'm not getting anywhere. So let's do the integral of this part. I'm going to leave the negative sign off and the half off. So what I'm going to do is I'm going to do the integral of e to the 2x cosine of x dx. So that's this part. I'll add the constant later. So you're like, oh, okay, I'll do it again. I don't think it's going to do me any good, but I'm going to do it again because he told me to. So u is equal to the cosine of x. Dv is equal to e to the 2x dx. Forgot my dx over here. So du is equal to the sine of negative the sine of x dx. So make sure I get the negative sign in there. Negative, okay. And v is equal to 1/2 e to the 2x, just like before. So I plug those in. You know, the integral of this u dv is equal to u times v minus the integral of v du. So I get the cosine of x times 1/2 e to the 2x u times v minus the integral of v, which is e to the 2x times du. Wait a second. Nope, it's v. I point to the wrong thing. So it's 1/2. So I'm going to have 1/2 e to the 2x, that's v, and du is equal to negative the sine of x dx. And then I can plug that in over here. So if I put this all together, well, it's going to be very small because I can fit everything together. So I start with my original integral, which was the left-hand side. So I get e to the 2x times the sine of x dx is equal to this term, which is going to be 1/2, take the 1/2 out front, then do the exponential function, then do the sine function, minus 1/2, so that's the negative 1/2, times this thing. So that's going to be negative 1/2 times cosine of x times 1/2 e to the 2x minus the integral of 1/2, and let's go ahead and take this negative sign, cancel those out, so that's positive. So you get 1/2 e to the 2x, 1/2 e to the 2x sine of x dx, close bracket. Let's make sure I did this right. So you get 1/2 e to the 2x sine x minus 1 half times the integral of this thing, which is cosine of x times 1 half e to the 2x minus the integral of 1 half e to the 2x, and the negatives cancel that. Okay, so there we go. And now if you are more observant than the average person, you'll notice that on the left-hand side we have the integral of e to the 2x sine of dx. On the right-hand side we have also the integral of e to the 2x sine x dx. So these are the same thing. So what I can do is I can move that to the other side and group the two terms that are the integral of the sine of this thing. And what you'll have is you've got negative 1 half here times positive 1 half. So that'll be negative 1/4. And when you move it to the other side, it'll become positive 1/4. So what we have is we'll have on the left-hand side, we'll have the original integral plus 1/4 the original integral. Okay, so that's the right-hand side. I mean, left-hand side. And then on the right-hand side, you've got 1 half e to the 2x sine x. And here we're going to have negative 1 half times positive 1 half, which is negative 1/4. So we get negative 1/4 e to the 2x times the cosine of x. And I forgot my plus c over here, plus c. Plus c. So you can see 1 times this integral plus 1/4 times this integral is 5/4 times this integral. So you get 5/4 the integral of 2x sine x dx is equal to the right-hand side. And so the final answer, you're going to multiply by the reciprocal. So you get the original integral which is e to the 2x sine x dx is equal to 4/5 times this thing, 1 half e to the 2x sine x minus 1/4 e to the 2x cosine x, whole thing plus c. Yeah. Am I going to put that on the test? Absolutely not. But it does give you an idea of just, another example of using integration by parts. Even in a case where you might not have thought you could do it. And it's because of the repeating nature of the derivatives, because the derivative of e to the x is always some constant, e to something x is always something times the original function. And when you take the derivative of the sine, you get the cosine, but then when you take the derivative of the cosine, you get back to the sine. And so that's something you can take advantage of. Okay, so we'll see you at 9:15 for physics.